Welcome to Chemical Process Engineers channel. In this video, we will discuss about pump basic definitions, net positive suction head and some methods to increase Npsh. Before we start design of pump or we start filling pump datasheet, learning about definitions related to pump and their significance is essential. First definition is pump head. It is a measure of maximum height a pump can lift the liquid or energy it imparts to the liquid. Typically expressed in units of length like meters or feet, it is important factor in selecting a pump for specific application. It represents the work done by the pump to overcome gravity and move the liquid vertically, and it is inversely related to the flow rate. For example, a pump with 5-meter head could theoretically lift fluid to vertical pipe 5 meters high from its outlet. Pump head is a way of quantifying the energy a pump transfers to a fluid. It indicates the pump's ability to raise a volume of fluid to a certain height against the force of gravity. Unlike pressure, which is measured in units like psi or bar, head is measured in units of length such as meters or feet. This is because pump's ability to lift fluid is somewhat independent of fluid's density. Second definition is pump capacity. It refers to the volume of fluid a pump can move or discharge over a specific period of time. It is essentially a measure of pump's flow rate, and it is typically expressed in units such as gallon per minute or meter cube per hour. Choosing the correct pump capacity is crucial for system efficiency, preventing energy waste and ensuring proper operation. Accurate pump capacity is needed to correctly size the entire pumping system. Selecting the right capacity prevents oversizing or undersizing, which can lead to higher energy consumption or insufficient performance. Capacity is used to create a system curve, which helps in understanding pump performance. Third definition is pump rotational speed. It is the rate at which a pump shaft and impeller rotate, measured in revolution per minute. It is a critical operating parameter that determines the pump's performance, with higher speed generally leading to increased flow rate but also influencing efficiency and potential issues like cavitation. This speed is set by the drive system such as electric motor and can often be adjusted using technology like variable frequency drives. Higher rotational speed result in higher flow rates. Adjusting the speed using VFD can optimize the pump's efficiency for specific conditions. The head or pressure generated by pump is directly related to rotational speed. For positive displacement pump, pump stroke is measured. Pump stroke is one complete unidirectional motion of the piston or plunger in reciprocating pump, moving a fixed volume or fluid for each stroke. This movement, often driven by rotating crankshaft, draws fluid into the pump on one stroke and pushes it out on the return stroke. The number of strokes per minute indicate the pump's rate of operation and can be used to control the amount of liquid being pumped. The total distance the piston or plunger travels during the single movement is known as the stroke length. Now pump requires power to increase the pressure of liquid, and the power that can pump actually add to the liquid is known as hydraulic power. A hydraulic pump converts mechanical energy from a motor into hydraulic energy by moving a pressurized liquid, and its equation is shown here. In pump, brake horsepower is the actual mechanical power delivered to the pump by the motor. It is the input power required to operate the pump at a given flow and head, accounting for mechanical and hydraulic losses, and it is used for selecting appropriately sized motor for the system. Brake horsepower equation is shown here. It is hydraulic power divided by efficiency. Brake horsepower is always greater than hydraulic power because of the inherent losses in the pump system. Pump efficiency is the ratio of energy delivered by the pump to the energy supplied to the pump shaft. Pump system can consume a significant portion of energy or power. Improving pump efficiency lead to lower energy consumption, reducing cost and promoting sustainable operations. Over long term, energy cost for driving such pump can far exceed the initial purchase of cost, and higher efficiency means least wastage energy is lost as heat or noise, improving the overall system's performance. Understanding these definitions help us design pump according to our requirement. Other important terms that help us design the pump are NPSH and total dynamic head. NPSH or positive suction head is a crucial parameter in centrifugal pump operation, and the definition is the absolute pressure head available at the pump inlet above the liquid's vapor pressure is called net positive suction head. Let's take one example to understand. As we can see here, one pump is used to transfer liquid from tank. As liquid flows into the pump and through the impeller, the pressure drops, especially at the inlet. If the pressure at any point inside the pump falls below liquid's vapor pressure at operating temperature, the liquid will vaporize, forming bubbles. These vapor bubbles can collapse as they move to a higher pressure area, causing damage and noise that is called cavitation. A sufficient net positive suction head at the pump inlet ensures that the pressure never drops below the vapor pressure, preventing these bubbles from forming. Here the equation to calculate NPSH is given. This equation includes pressure in tank, pressure due to static head, velocity head, frictional pressure drop, vapor pressure head. In this equation, vapor pressure head to be considered at pump suction I or pump inlet. Pressure in tank as head is due to pressure present inside the tank above the liquid level. It can be atmospheric pressure in atmospheric tank, and in pressure tanks it can be higher pressure. As this pressure increase the NPSH value, it is added into the NPSH calculation. Static head is the pressure due to height of liquid level compared to the pump center line. It can be derived simply by multiplying height of liquid level compared to pump center line, density of liquid at given temperature and gravitational constant. If the liquid level is above pump center line, then the height difference considered positive, but if the liquid level is below pump center line, then the height difference considered negative. As this pressure increases the NPSH value, it is added in the NPSH calculation. There are multiple pressure drop available in pump suction line, and they are calculated as velocity head lost. For example, different type of valves, elbow, bends, strainer, NRVs, and instrument like flow transmitter can be present. This pipe fitting pressure drop can be calculated using two methods: equivalent length of pipe for fittings and valves, and number of velocity heads K lost in pipe. In first method, pressure drop due to pipe fitting, same as frictional loss, is equivalent straight length of pipe of same size is considered, and all equivalent length of fitting are added to consider final calculation. In second method, equivalent number of velocity heads lost in pipe for pipe fitting is added to consider total pressure drop in suction line. As this pressure drop decreases the NPSH value, it is subtracted from the NPSH calculation. Frictional head is the pressure drop due to pipe frictional losses. Here equation to calculate the frictional head is given, and it is called Darcy equation. Friction factor is a function of Reynolds number and the roughness of inside surface of pipe. Now Reynolds number is less than 2100, that means that the flow is laminar type, and for the laminar type flow, friction factor can be calculated using F is equal to 64 divided by Reynolds number, and if the Reynolds number is greater than 2100, that means that flow type is transition flow or turbulent flow, and for transition flow or turbulent flow, Moody diagram is used to find the friction factor. Find relative roughness value by dividing diameter of pipe from roughness of pipe. Roughness of pipe value given in the chart for different MOCs. Using this relative roughness value and Reynolds number, we can find frictional factor value from Moody chart. And this friction factor value is used to calculate frictional head. Now frictional pressure drop decreases the NPSH value. Therefore, it is subtracted from the NPSH calculation. Using all this calculation, we can calculate NPSH available. NPSH available gives value that is available to pump by the system. It can also be calculated for design system using piping isometric. NPSH required value is the value that is provided by pump manufacturer, and this value is required to operate without cavitating and damaging the pump. It is determined by pump's internal design and operating characteristics. To prevent cavitation, NPSH available must always be greater than pump's net positive suction head required. If NPSH available is less than net positive suction head required, the pump will experience cavitation leading to severe noise, vibration, reduced flow, and potential damage to the pump. When we calculate NPSH, its value is lower and we can increase the NPSH using different methods as shown here. Instead of using atmospheric pressure which is not in your control, you can increase pressure in tank. If the pump only starts to cavitate near the end of emptying the supply tank, you may consider allowing for a higher level of liquid to return. Raising the tank or lowering the pump helps but may not be feasible. You can decrease the frictional loss by increasing the size of the suction piping or decreasing the length, reducing the obstructions such as valves, strainers, and other fittings. For thicker liquids, heat tracing the line will help to reduce the viscous loss. Hoses and corroded pipes have higher losses. Consider replacing with new pipes. Also, control the temperature to make sure the vapor doesn't get too high. Often tanks and pipes holding the high vapor pressure liquid are painted with light colors to avoid sun hitting and then raising the vapor pressure. Hope you have find this video more informative. To learn more about pumps, see other videos uploaded in the pump series.